we're now going to look at how to transform functions, and specifically we're going to go and transform the parent graphs that we've talked about. So we had a graphic organizer that had them listed. We also looked at them in some notes. So we're going to take those parent graphs and move them all around according to the letters we already looked at, A and B and C and D. So I'm not going to relabel those because they do exactly the same things as what we had before. But F, right here, F is now going to be replaced with a specific function. So it's a specific function that we're going to go through and we're going to use. So if I come down here to example 1, when I look at example 1, I notice right away that I'm living in the absolute value function family. Whoop, let's scroll back down. There we go. Absolute value function family, right there. So I know that my shape is a V shape, and it has not been reflected left, right, or up, down. So I have a V shape as my graph. I look at the X, Y, and I know that my transformations are going to be X plus 5, because I'm moving right 5 from right there. And then 2Y plus 6, because I have the multiplication of the stretch factor, and I'm adding 6 on here at the end. The key is, now I don't have necessarily a graph right before this one to go back to. I've got to go the whole way back to my parent graph. And if I go to the parent graph of an absolute value, I find that it goes through 0, 0, 1, 1, negative 1, 1, and you can keep going if you want with more. A lot of times 3 points will give us a good look at what this function looks like. So I take those points and I run them through my filter right there, and I see 0, 0 comes out as 5, 6, 1, 1 comes out as 6, 8, and negative 1, 1 comes out as 4, 8. So I go to 5, 6, give myself a dot. I go to 6, 8, give myself a dot, and 4, 8, and give myself a dot. So I have my V shape coming down through those and traveling up through the other points, and there's my transformed absolute value graph. For the domain and range here at the bottom, I just look at the graph and notice the domain is negative infinity to infinity, and the range starts at bracket 6 and is going to travel the whole way up to infinity. Just a little bit of extra information when I do this. Looking at example 2, for example 2, I have a square root graph. So now I'm living in a family where the parent function looks like this. He starts at a point and goes. But I have a reflection. I have that reflection right there. So I reflect this graph upside down over that x-axis, since the negative's on the outside. So when I do that, my shape's going to look like that. So I just keep that blue shape in the back of my mind. That's what my points have to go through, that kind of shape. If I find my filter here, this is going to become x minus 7 because I've been moved left 7, and negative y minus 2 because I've been reflected and I'm moving down 2. So square root, go back to the square root graph. 0, 0, that's the starting point. 1, 1, something like 4, 2. You could do 9, 3 if you want. I'm just going to stick with those 3 for right now. Run each of those 3 through that filter, so I get negative 7, negative 2. I get negative 6, negative 3. I'm just plugging the x and y in. And I get negative 3, negative 4. Plug x in for x, plug y in for y. So when I graph this, negative 7, negative 2, negative 6, negative 3, and negative 3, negative 4, fits the shape that I had, and the shape that I wanted. So he's going to come down and keep curving some and go like that. So there's my square root transformed graph. The domain, according to the graph, is going to be negative 7 to infinity, and the range is going to be negative infinity the whole way up to negative 2 with a bracket. So there's my transformed graph and the domain and range. Again, the key is just go back to your parent graph and see what the parent graph was. 2 more examples that I'll just run through. Example 3, we have a parent graph that is a cubic function. So my parent function looks something like that, just in a sketchy way. It has not been reflected at all, so my graph now is going to look about the same. If I look at how these points have been changed, my xy becomes x plus 4, because it's been moved right 4, and 1/3 y. So I have a vertical shrink, so my graph should get shorter and probably wider. If I go back to the parent graph of my cubic function, I know that 0, 0, 1, 1, -1, -1. I'm also going to do 2, 8, and -2, -8 in this case, just to get a better idea of what it looks like. 3 points would be enough, but these points will be much better and give me an idea of what my graph looks like, just to make sure I get the shape right. So 0, 0 becomes 4, 0. 1, 1 becomes 5, 1/3. -1, -1 becomes 3, -1/3. 2, 8 becomes 6, 8/3, and this becomes, plug in the -2, I get 2, 8/3. So there's my ordered pairs, 4, 0, 5, 1/3. You can kind of see why I chose to do more points, because it's hard to even graph some of these points. 3, -1/3, and I get 6, 8/3 is 2 and some. There we go, 2.6-ish. And negative, I missed a negative sign there, -8/3 should be down here. And it gets me a good idea of what this graph looks like. He's coming up. He almost kind of levels out slightly there before he goes back up. So there's my transformed graph. I used a lot of points to make sure I get a good look at it. The domain and range are both going to be -infinity to infinity. And our last example for the first set here is a cubed root function. So if I go back to a cubed root, I know that cubed roots look like that typically. But since he's been reflected right there, my cubed root is going to be flipped upside down. So he's going to be going down and over. Again, that's just a rough sketch so I can see what the graph should look like. My filter that I'm going to run everything through is just x, nothing's happened to the x values, and -4y plus 5. Go back to the cubed root parent function, and I can get 0, 0 as a point, 1, 1 as a point, and -1, -1 as a point. We could try to do some more. They might not fit on the graph, depending on which ones I choose. I'm just going to do it with these 3. 0, 0 becomes 0, 5. 1, 1 becomes 1, 1. It doesn't really go anywhere. And -1, -1 becomes -1, 9. So I have 0, 5, 1, 1, and -1, 9. And this is where knowing the shape really comes in, because a lot of people would like to make it go something like this, like that, but that would be a cubic function. We're dealing with a cubed root, and I know based on my shape up here that it's going to run a lot more horizontal and come down. Now, it never goes fully horizontal, but it's not going to be as vertical as a cubic function. So again, his domain and range, just like the previous one, are both -infinity to infinity. And there we go. So looking at what's the transformation, and then going back to the parent graph to find both the shape and the initial points I should use will get us a really good idea of what these graphs look like.